Okay. I saw the list of formulas that they're going to let you take on a card.
Yeah. No, those are the formulas that they're already going to have on the sheet, not including the ones they're going to have on the card.
All of these formulas here, yeah.
Yeah.
Yeah. Okay.
And in addition to that, I also get to make my own card. So maybe
you get one index card additionally. Okay, I didn't know that.
Yeah.
Hold on.
Yeah.
Got my dog up, closing that door. All right. Well, let's look at these quickly. What's number 1 equal to?
X2 x squared y wait.
Always do these in 2 steps. First step, subtract the exponent. Do the same with the y's.
So it's y negative 1?
Now,
Y to the negative 1?
Now, they don't like negative exponents in their answers, so what's that the same as?
Just y.
In the denominator. In other words, y to the 1. So this is going to be the correct answer because it's got both positive exponents.
Why does it matter? Is to the first power, does that matter?
It doesn't really. In other words, there's nothing wrong with that answer there.
Yeah.
If you said y to the negative 1.
Yeah.
It depends on the teacher. If the teacher has specified that they want your answers with all positive exponents, then you would need to give it like that. But
I don't think it's like that.
Okay. If they don't care, then this is fine. Either one of those.
Okay.
Next function, does that represent growth, decay, or neither?
Decay.
Yeah. If that's less than 1, it's decay. If it's greater than 1, it's growth. If
How can it be neither?
1,
oh yeah, 1.
Exactly 1. Then you would have a graph that looked like this.
Yeah.
In other words, if it was 1, then 1 to the x power is always 1.
Mm-hmm.
All right. Scroll down here. Now, tell me the general formula that applies here, because there's 3 different formulas for earning interest.
Is it the f of x thing?
Well,
no, I don't really remember the formula, but I do remember how I would do it.
Okay, how would you do it?
Well, it's not really a formula though. I'd take it's like you times 4,000 by 0.09 and then take that and times that by 0.095 and then do that 5 times.
That's the hard way to do it.
Yeah.
After 15 years, you wouldn't have been able to do it that way.
Yeah.
So knowing the formula, by that I mean your principal is going to be what you started with, a sub 0, times 1 plus the interest rate to the t power.
Yeah. I remember
so it's equal to, and this is the way you should almost start every math problem. Seriously. If you can start a problem with the general formula, then it becomes a piece of cake, because then all you're doing is plugging in the numbers.
Yeah, I got to make sure I know all the formulas. The ones that I don't have on my already given, I'll probably put on my note card.
Well, this one's on the already given.
Okay, cool.
Okay. And this is for yearly compounding. And that's
Yeah.
one of them is for yearly compounding. The others are continuous compounding, which is a different formula, and greater than yearly, like monthly or daily. Each of them have their own formulas, all three of those. So it's not so important that you remember the three formulas as long as you know which formula to use.
I think we're only using the yearly one though.
Yeah, you're right. This first one is the only one they list, which is the one I used.
Yeah.
Okay, so you don't have to worry about continuous compounding, and you don't have to worry about like monthly compounding. So as long as yearly compounding is the only one they ask you about, then this is the correct formula. And it says plus or minus because if it's
a negative,
if it's
a decay,
like a car depreciating, then R would be a negative, or well, it would be 1 minus R. You say a car depreciated by 10% every year. Well, then it's going to be minus 0.1 instead of plus. Plus is for appreciation, minus is for depreciation.
Okay.
Rule of log allows me to combine those two into a single log expression.
Is it just log 316?
Not 16, you're close. You don't subtract, you divide.
Oh, so it's
log base 3 of 20 divided by 4. Or log base 3 of 5. That's the answer they want. The thing to remember is that logs are exponents. So you have to use the rules of exponents. In other words, if I'm subtracting two logs, what I'm really doing is dividing their argument. If I'm adding two logs, I say what's the log of A plus the log of B, what's that equal to?
Log of A plus log B?
No? Yes. What is that equal to?
In
terms of a single log.
Log A plus B?
Not A plus B. It's never the same. It's always different.
Oh, A times B?
Yeah. In other words, if I am multiplying in the argument, then I'm never multiplying the logs, I'm adding them. If I am dividing in the argument, then I'm never dividing the logs, I'm subtracting them.
Yeah, okay.
If I'm exponentiating, if I have the log of A to the B power, then I am multiplying. The thing to remember is you're never doing the same. If you find yourself taking the sum of two logs and adding in the expression, then you're doing the same. And never do that with logs, ever. All right.
So when it's exponential and when it's addition, they both end up multiplying? Or is it different?
Multiplication turns into addition. Division turns into subtraction.
Yeah, I mean, because for addition, addition turns into multiplication, right?
Well, it depends on which way you're going. Yeah.
Oh.
You start with two log expressions that are being added. Yes, that turns into a single log expression where the two arguments are being multiplied.
Okay.
In other words, the log of 3 plus the log of 2 is the log of 6. It's the same as the log of 3 times 2. Mm-hmm. But the one thing you just have to remember is you're never doing the same thing. If you find yourself doing the same thing, you're making a mistake. In other words, when I originally asked you this, you said, well, is it just the log of 20 minus the log of 4? Well, it isn't, because that would be required that you do the same thing.
Yeah. Okay. Let's try number 5, I guess.
All right. Now, most exponential expressions, which is what that is, and it's an exponential expression because the variable is in the exponent. That's what defines an exponential expression. Now, 90% of the time you have to use logs to solve these. But every now and then they'll give you one where you can find a common base between 5 and 125. What's the common exponential base?
25.
Actually 5.
Or no. Yeah, 5. That's what I meant. So I already solved it in my head because it's kind of simple, I guess.
Well, it is. This one's pretty simple, but they're certainly not all this simple.
Yeah.
But the thing is, you still want to do it methodically. In other words, I want to write 125 as 5 to the third every time.
Yeah.
Now, what can I say? If 5 to the 2x minus 1 equals 5 to the third, what must be true?
X is 2.
Well, 2x minus 1 is 3, which makes x equal to 2.
Yeah. X equals 2.
I know. I just don't like skipping steps. I'm a firm believer that skipping steps is the fastest way to make mistakes.
Oh, okay.
If you do it one step at a time, then you won't make any mistakes.
Uh-huh.
Now, how about this one? Number 6.
Log 5x minus 4 equals log 525. Well, would it be 29? I don't think that's too simple, right?
Well, and it's also, no, it wouldn't be 29. However, what I could do is subtract the right side from both sides so that I have this. Log base 5 of x minus log base 5 of 25. And then if I put the 4 on the other side, I can get to that step. See how I get there?
Uh-huh.
Now combine those into a single log expression.
It would be dividing, so it'd be log 5x over 25.
Yeah.
And then if that is equal to 4, then...
Now turn that into an exponential expression, and you'll be able to solve it easily. How do you turn a log expression into an exponential expression?
I'm not sure.
Number on the far left.
Yeah, put the 5 over them.
Power of the far right equals the number in the middle.
Oh, okay.
So we got 5 to the 4th power equals x over 25. And now we have an algebraic expression that you can solve using algebra.
Mm-hmm.
Okay.
So 5 to the 4th power is
625.
625. Yeah, I think so. Yeah, 625. So x has to be 4, 8, 12, 300. Okay. I'm doing too much in my head.
Right. You got a calculator in front of you?
Yeah, I can get it up on my phone really quick.
Use it to solve that. You don't have to do that in your head.
So, 625 divided by 25.
Not divided by, multiplied by 2.
Oh, yeah, man. Sorry. 15,625.
Okay. And that's what x is. In other words, the secret on all of these log equations is to combine the log expressions into a single expression.
Wait, why is it 600?
What? 2 log expressions.
No, wait. Why is it 625 times 25? Oh, yeah, because it's x over.
Yeah, because it's x over 25. Now, that's assuming that I read this, perhaps incorrectly, but I read this, there's no parentheses around that. In other words, that is a different expression than what they wrote. They wrote the log of x minus 4 is not in the argument, equals the log of 25. Okay? The answer would be different if that was a single argument. In other words, if they meant to put parentheses around that. Now is all I got is x minus 4 is equal to 25, so x is 29. But they didn't. Shows you the difference in parentheses. In one case the answer is 29, and in the other case the answer is however many thousand you got.
Uh-huh.
So parentheses are very important.
Mm-hmm.
All right, let's go on. Do you have any other questions? We probably ought to get the questions out of the way with like logs. You mind if I make up some? I can make up
Sure. Sure, make up a couple.
Well, or at least a simple one that.
Yeah.
There, they don't get much simpler than that. Always solve that for x.
That would be, x would be what, like?
Well, you gotta know the method, because x is clearly greater than 2 and less than 3, right?
Is it 2.3?
No.
Repeating? No.
You can't.
Is it 7 divided by 2?
You cannot solve this algebraically. That is an exponential equation which cannot be solved algebraically. The way I'm going to solve this is take the logs of both sides. Always. Now, what can I do with the x? Once I've taken the logs of both sides, what can I do with that x?
Put it down?
By down, you mean in front, like that.
Yeah. Yeah.
And that's huge. That's one of the most important properties there is about logs, is the ability to turn it from an exponential equation into an algebraic one. Notice that that is now an algebraic equation. And x, remember these things are just numbers. So I'm dividing both sides by natural log of 2, and there's my answer. I don't want it as a decimal, nor does your teacher. This is the most precise answer you can get.
Uh-huh.
Okay?
Okay.
When you have exponential, I can't believe they didn't give you one here, similar to this. They gave you all logs. The one exponential they gave you, we didn't need to use logs to solve it, because it happened to be the type where the exponential base for 5 is the same as the exponential base for 125. So you don't always have to use logs, but gosh, 99% of the time you have to use logs to solve these things. because there was no common exponential base. In other words, if I go back to my original problem, 2 to the x equals 7, there is no common exponential base between the numbers 2 and 7. I cannot write 7 as 2 to some power. So the only way to solve this, if that was an 8, it'd be different. I wouldn't need logs. I'd know that x had to be 3. But the fact that it's a number other than a base 2 number means you need logs to solve it. All right, let's go on.
Okay, I need just 2 seconds. I'll be right back. Okay.
All right, inverse functions. Well, first of all, let's just talk about how you solve for an inverse function. There's really only 2 steps. What are they? In other words, they give you this up here, and that's a true statement, okay? But that doesn't help for solving this problem. That's not going to get us far for solving this problem. That's only going to prove that what we come up with is the inverse if we want it. But there's 2 steps. I say 2. First of all, make it an equation of y, not f of x. So that's my first real step. Sometimes they'll give it to you like this, so you don't have to do this. But you understand that the notation f of x is the same as y. Okay. Now, the 2 steps are switch the variables and solve for y. 1, 2. Okay? So first step, what is the equation?
If you switch the variables,
yeah, what do you get?
x equals 5y plus 8.
And now solve that for y.
Y.
Not in a single step. Do it in multiple steps.
I don't follow at the moment.
How do you solve for y? If I tell you x equals 5y plus 8, how do you solve for y?
Y equals 5x plus 8?
No.
Or,
just
wait.
Do it piece by piece. Don't try to come up with the whole answer at once. If I'm trying to isolate y, which is what I'm trying to...
Divide by 5?
Well, it's always a better idea to get rid of what's being added and subtracted before you do the handling of the division or the multiplication. So the first step is to subtract 8.
Subtract 8.
That gives you that. Now what?
Now divide by 5.
Yeah. So that's our answer. And I've solved for y. Now, the only thing is it's not really correct to call it y because it's not the same as that y. This is y inverse. So when I finally get to the answer, I might put a y inverse. I might even write it like this. Go back to the f of x notation that they started with. And now I'm perfectly correct. In other words, that is the inverse of that. Don't guess. They're too hard to guess because a lot of times they don't really resemble the original function at all. You have to do it step by step. Just remember, switch the variables and solve for y. Now, in reality, you can do those 2 steps in either order. You can solve for x and then switch the variables, That'll give you the same answer.
Uh-huh.
But I always like to do things the same way. That's the secret to memorizing math. Don't mix up your methods. If you're going to switch the variables and divide and solve for y, always do it that way.
Uh-huh.
Okay? Now, we're still doing just half-hour sessions here.
Yeah, I think I'm going to book an hour session next, though.
Okay, that's fine.
You want to just, I'll just book it now, and
Yeah,
I'll,
let me show you my schedule. There it is. I got everything.
okay. So you got me for Thursday. On Thursday, put it to an hour.
Okay, from 4 to 5, we'll extend it an hour.
Yeah. And then on Wednesday, give me another half hour.
At what time? 4 to...
Same time, yeah. 4 o'clock for you.
Or 4 to
4:30. Yeah.
Oops.
And I think this weekend I might even have a little session too.
Okay, like I said, the more the merrier for me. Hold on, if I can spell your name right, I'll be... the first 3 letters or it doesn't recognize it. Okay. So I got you tomorrow from 4 to 4:30, and I got you Thursday from 4 to 5, and if you need more after that, I've got the whole week of it.
Okay.
Okay? All right, Don.
Yep.
Have a good night. Talk to you tomorrow.
Yep. I'll see you tomorrow, Mr. Cowan. Have a good one.